Welcome, welcome. In the last lesson, we learned what continuity meant, and today I want to look more into which types of functions are continuous and where, and we're going to start with a theorem that says that many of the functions we've been dealing with so far are continuous on their domains. Let's take a look. So, we have a theorem, and it says the following types of functions are continuous at every number on their domain: polynomials, rational functions, root functions, trigonometric functions, inverse trigonometric functions, exponential functions, and logarithmic functions. This is incredibly useful because if we need to evaluate the limit of one of these types of functions as x approaches a number, if that number is in the domain, we can use direct substitution to figure out the value of that limit instead of having to make a table of values. Now, of course, this isn't going to solve all of our limit issues because there are so many situations where we're looking for a point that's not in the domain and we have to use tables of values, or we have to use the other limit properties, or we have to simplify things, which sometimes involves different sorts of strategies. So this isn't going to be a silver bullet that solves everything, but this will, in many circumstances, allow us to evaluate a limit by simply evaluating the function for the given value of x. So lots of situations where this saves us some work. But then, what happens if we have a function where maybe part of it is a trigonometric function, but then there's also an exponential function added to it? Or maybe it's divided by a logarithmic function or something like that. Well, we have another theorem that's going to help us out there. This one says, if f and g are continuous at the number a, and c is a constant, then the following functions are also continuous at a. And we have f plus g, f minus g, a constant times f times g, and f divided by g, so long as the denominator is not 0 at that value a. So this means that we can take functions that are continuous and we can add them, subtract them, multiply them, divide them, multiply them by constant coefficients, and the results are also going to be continuous. So we've got all sorts of combinations of different functions that end up being continuous on their domains, which then allows us to use direct substitution there. So let's take a look at a couple of examples where we can use these properties to our advantage. Let's find the limit as x approaches -2 of the rational function x cubed plus 2x minus 1 over 5 minus 3x. Now here, because x equals -2 is in the domain, doesn't give us a denominator of 0, we know that we can just directly substitute this in because this is a rational function, so it is a continuous function, and that means that we can evaluate the limit by just substituting that value into the function. So that's going to be -2 cubed plus 2 times -2 minus 1 all over 5 minus 3 times -2. -2 cubed is -8, and then we've got minus 4 minus 1 all over 5, and then -3 times -2 is 6, so that'll be 5 plus 6. And then that numerator, when we add those together, we get -13 all over 11, and so that limit is equal to -13/11. Let's look at another example. This next one will ask us to find the limit as x approaches pi/4 of tangent of x. Now, tangent of x is a trigonometric function, So it is continuous on its domain, and pi over 4 is in the domain of tangent. And so that tells us, because it's in the domain and it's continuous on the whole domain, we can evaluate the limit by just taking tangent of pi over 4, which is 1. So that limit is equal to 1. Pretty good. Let's take a look at another one. Let's find the limit as x approaches pi of sine of x over 2 plus cosine of x. Now, this is not a single trigonometric function, but it is made up of a combination of trigonometric functions and a constant function, which is an example of a polynomial, a very boring example, but an example nevertheless. And so if we take two functions that are continuous and add them together, we get another continuous function from this second theorem. And these functions are all continuous for all real numbers, so we don't have any domain issues there. So the sum of two continuous functions is a new continuous function, and then a quotient of two continuous functions is continuous, except where the denominator equals 0. But 2 plus cosine of x will never equal 0, because cosine of x is never negative 2. So that means that this new combination of functions is a continuous function for all real numbers. And so that means if we want to find the limit, we can just evaluate that at pi. So we've got sine of pi over 2 plus cosine of pi. And sine of pi is actually 0. And then we've got 2 plus cosine of pi, which is negative 1. And so that's going to be 0 over 1, which equals 0. So that limit is equal to 0. Now I've got one more theorem and then one more example for us to take a look at. So let's look at them. If g is continuous at a and f is continuous at g of a, then the composite function f of g, given by f of g of x equals f of g of x, is continuous at the value a. And we can use this in an example. Find the limit as x approaches 0 of sine of the quantity x squared plus pi halves. Now here, this is not a combination of functions covered by this theorem where we're adding two functions or subtracting them or taking the product or the quotient. Here we're taking the composition of functions, meaning we're taking a trigonometric function and evaluating it with an input of a polynomial function. So this is a composition of two different types of functions. And this says that this composition of functions is continuous at a value so long as the inner function is continuous at that value a, and the outer function is continuous at whatever the inner function is evaluated at a. Now, x squared plus pi over 2 is continuous everywhere, and sine is continuous everywhere, so this composition is going to be continuous everywhere. Specifically, when x is 0, it will be continuous, and so that means that to evaluate the limit, we just evaluate the function by plugging in 0 for x. So this becomes sine of 0 squared plus pi halves, which is the same as just sine of pi halves, which is equal to 1. So we know that this limit is equal to 1.